Okay. Okay. Okay, so this is a continuation of the overview. I'm still not getting into a particular NDE method. Oh. So, let's look back at the generic NDE system from morning. We have all these different components. And one of the things, the overall research in the overall NDE system is broken up into these areas. There is a modeling component. Again, we will talk a little bit about this. There are modeling can be analytical or numerical, and there are a lot of challenges even when you're looking at the modeling of these processes. And this is typically referred to as the forward problem. And in inverse problem, you have issues like defect classification, characterization, and you've got to do a lot of signal processing in these. You've got to take into account what are the uncertainties in a practical system, and so on. So let me put this in this context of the generic NDE system. So in the forward problem, you know what is the excitation source, you know the sample geometry, and you're predicting the measurement signal. That's called the forward problem, going from here to here. And the inverse problem is given the measurement transducer signal, which is processed a little bit, taken out, or you take out all the noise and everything. And you also know what was the excitation that was sent into the sample. You try to determine what is the defect, what's the shape and size of the defect, and so on. And of course, you then use the output of this inverse problem in a structural mechanics model and determine the remaining useful strength. So this part is the inverse problem. So inverse problem, you have to deal with processing the measured signal, and then some specific algorithm. How am I going to detect what is the defect shape given what is the output signal, and also what's the input signal. So those are basically that. So the areas of research here in the forward problem, as I described, you want to determine the NDE sensor signal given the excitation source and given the defect. You know there is a sample, you know what the defect shape size is, and what kind of signal will be produced by this situation. So the typical solutions when you for this forward problem, you can, because what the underlying governing equation is. If it's an electromagnetic, you have the field, Maxwell's equation, and if you have ultrasonic, you have the whatever equation mechanical engineers use for the wave propagation, elastic wave propagation. And those are all essentially differential equations. And you can solve differential equations analytically, or you can solve them numerically. And analytical solutions have, are simple. They have a lot of advantages. We'll just look at it in a little bit. And the other area of research in NDE is the inverse problem. So given a transducer signal, that is the NDE measurement and the test geometry, what is the flaw image, the defect image? So that's what you want to determine. So in general, inverse problems are what they call ill-post. That means you can have two different defects which will produce the same signal. So the signal is perturbed a little, and you can have defects which can be very unstable, the algorithm. And also in NDE, you have two types of inverse problem. One is you take the signal and you just want to classify, is this a defect or is this, and I'll give some examples of the different classes which depends on a particular application. And the other type of inverse problem is determining the entire profile of the defect, of the defect geometry. And so you reconstruct the flaw profile, which is called the full solution. The other area of research in NDE is also instrumentation. So very often for a particular type of a problem, you want to design the best kind of sensor. You want to optimize the sensor design and the system design, and then the data analysis. Algorithms can also be part of the system. And I will talk about an example of this. We have developed two such systems. One is for detecting cracks under fasteners in multi-layer geometry in aircraft. And the other is the heart valve inspection. I think we talked about it quite a bit this morning. Okay. Okay. So let's talk about the area of research which I call the forward problem. This forward problem uses simulation models. Okay, the typical solution approach, of course, is every differential equation has an analytical solution. But analytical solution for solving differential equation is only available if you have a very simple geometry. All the boundaries are parallel to your coordinate axis, and the flaw also is, has a nice circular shape. Then you can develop an analytical solution. But in general, when you consider a multi-layer geometry and arbitrary shape crack, you cannot develop analytical solution for this. You have to go into a numerical modeling. But once you have a model, a forward problem is nothing but you have a simulation computational model for your system. Such a model can be used for a variety of purposes. Okay, you can not only solve the forward problem, you can actually visualize how the flux, the field is distributed in the sample, and you can use it for optimizing the sensor. And also a model can be used as a test bed for generating, you can't fabricate a subsurface flaw, for example. But you can do that using the model, generate the signal, and use that for training your pattern recognition algorithms, okay? And so on. So we, I think, do have the last day, we have one lecture on the modeling. Okay, so this again on forward model, all NDE processes, whether it is fall under one of these three different class of differential equations. You can have, for example, when you have magnetostatic, we have an elliptic equation that is shown over here. If you have eddy current, which is a diffusion equation, also you have thermal equations or diffusion equations. So you have a first order derivative of time derivative. And microwaves, ultrasound, all belong to the wave equation. So these are the different physical process: a diffusion, static field, diffusing field, and a wave propagating field. And these are the different NDE processes. These are the different typical governing equations. So once you have a governing equation, you know how to solve it, but you can solve it analytically only for very simple geometry. And in real world, you don't have simple geometry. Okay. So basically, when you talk about analytical models, the two major types of analytical solutions or analytical models are the volume integral equation and the boundary integral equation. And you all know that these kind of equations need what is called as the Green's function, right? And the Green's function is nothing but the solution to this equation when the source is an impulse. It's like an impulse response of a linear system. So to get the Green's function, I have to solve this anyway. So in volume integral and boundary integral, which depends on Green's function itself, one of the problem is how do I find the Green's function itself? But the advantage is that you have a closed form solution, and such a closed form solution is very useful for doing a variety of processes. Right. You have some, if you look at any textbook in electromagnetics, you'll have Green's functions for different equations in free space. Once you put in a sample, you already have interface. And you have to have, how do I incorporate that interface conditions into my overall model, okay? So the Green's function changes. And you put a crack in it, it changes, you don't even know what the Green's function is anymore. So it gives you some kind of an approximate solution. It doesn't give you an exact solution. Whereas numerical models, mainly the finite difference, finite element type models, can give you accurate, it's approximation in the sense that you're approximating a continuum by a discrete set of points, but you can always discretize it fine enough and get an accurate solution using finite difference or finite element models. And also the other thing is that developing a finite element model in 3 dimensions, it also, you have a matrix of the dimensions million by million or maybe more, and so it takes long computational times. But you don't have to worry about the complex geometry. You don't have to worry about nonlinearity. Whereas again, Green's function is inherently a linear method, and if you have a nonlinear material, you can't model it using analytical models. So those are some of the advantage, disadvantage of this thing. So numerical models are very versatile, and you can do all kinds of model. And I'll show some examples also in the last day. So some of the challenges, or particularly when you have nonlinearity, how do I introduce nonlinear materials into my finite element model? And if you have coupled models like thermoelectric or electromagnetic acoustic, those are modeling challenges. And the other thing is, if you look at a particular geometry, if you have pipelines, for example, pipelines are like 2 feet in diameter, okay? But you're looking for a hairline crack. So that your discretization should not be unstable. You have to be able to discretize a tight crack as well as a large sample. You can have moving boundaries when you're scanning, for example. You have a moving boundary problem. So that means at each position you have to overall build the whole thing and redo a lot of you do a lot of repetitive work. So those kind of problems, and then you also have effect of uncertainties. How do I model that? Okay, I'll talk a little bit about that too. One example is, we did some modeling for pipeline inspection. So basically, this is the pipe wall. We are looking for defects in the pipe wall. And in this inspection system, you have a permanent magnet, you have brushes, you have pole pieces. And so all of the, and so basically, you have not only the nonlinearity of the pipe material, but you also have the pipe, how does the permeability of the pipe material change in this direction when the field is in this direction? So there's some kind of non-anisotropy. So there are a lot of things that the model has to take into account. But again, it's a lot of work, but it can be done. And in fact, what we see here, this is again an important step when you do modeling, that is validation. So here we see a comparison of finite element signal with experimental flux leakage signal. If the comparison is this good, then the model is very valuable. Otherwise, it doesn't. Here's an example of model validation of experimental, of eddy current signals. So the geometry is this. You have a tube, and you have a defect here, and then you have a structure over here. Most realistic geometry will have some kind of a mechanical structure. It's not a defect, but it will produce a signal. Okay? And as you change this, the distance between the defect and this structure, your signal changes. Okay? So when you're far away from the support structure, you get only the defect signal. But as it gets closer and closer, as the D reduces, I think the D is mentioned over there. This is a case when D is 0, the defect is right in the center. And as the D increases, or rather, yeah, as it goes away from here, you can see things changing quite a bit. Significance of? The signal, oh, sorry, it's the eddy current signal. So you have basically a tube, you have a defect, and have a coil that is moving inside the tube. Okay, sorry. Yeah, I just wanted this. We'll talk about eddy currents, and I'll bring this up again at the time. So these are actually model-based, where I can, in a controlled manner, I can change D. And these are the actual experimental signal. And I think this is the same D as this. Where's my glasses? Can't see. The second plot down is 20. Yeah. Where was this? It's a pointer here. So this is D is 25, this is 26. So you should compare for validation. This is 20 and 21. Let's look at another one. This is 5.7, and this is 5. And this is 0 and 0. So you can see that this is the defect signal, and this big one is the signal from the support structure. And you get something very, so this is just an example of validation. Okay. This model, again, we use a finite element model. I see a lot of gaps, holes in this particular slide. I didn't make things very clear. I just pulled this for model validation, but most all the modeling that we have done in our group is using finite elements software. Yeah. Yeah. In this particular slide, what you're seeing is a very qualitative comparison, right? Yeah, it's unlike the previous one where you can see point by point matching over here. I have not shown that. This was just to show generally the trend, the model is working well, it's producing similar type of signals in a qualitative sense. Okay. But in many applications, yeah, you would need a point by point match. And in fact, for the same, we are working with the Electric Power Research Institute for the nuclear power plant. This tube that you see here is actually a heat exchange tube in a power plant, okay, for which we can use a particular type of eddy current probe. So I've not really described the sensor, what is the signal, and what's the e-simulation model. In this overview talk, I'm just giving you an example of validation. What is experiment and what is model-based signal, and you have to make sure that the model is right before you can use it for anything, right? That's all the point of this slide. I know that all the questions are very valid, and we will talk more about it when we go into the eddy current lecture.
Yep. Are there something like that the hysteresis loop that we have, that type of analysis?
No, this is linear. There's no hysteresis because it's not magnetic. Nothing is magnetic. It's just the eddy current signal. It looks like, this is again, tomorrow when we talk about magnetic materials, magnetic method, that is for magnetic materials, which has hysteresis in it, and it's a nonlinear model, all kind of problems, yeah. But this is nothing to do with hysteresis. This is only, in this overview talk, I'm saying modeling is an area of research and what constitutes a numerical model and what we need to do. And in fact, one of the advantage of model, I'm just giving a big picture, and then we'll go into things from the next 4 days. Okay. So the model is again useful for studying the sources of variability. Okay. What do we mean by variability? If you look at if you conduct an eddy current experiment, your liftoff can vary from one point to another point. Okay. Your probe canting angle, so when it's moving inside, the probe can wobble, there can be a different angle. Even if it's on a plane surface, there can be a slight amount of wobble that will produce a difference in the signal. The conductivity, the model uses a particular value for conductivity, but there can be a variation in the conductivity of the actual conductivity of this sample can be slightly different. Permeability, similar thing. And when you have an experimental system, you have instrumentation noise. The instrument can drift. That produces a different defect, and human factors. So it is inevitable when you do any kind of measurement or any physical thing, there's going to be variabilities or uncertainties. In the case of magnetic flux leakage, you have liftoff can vary. And we just pointed out the hysteresis because of the magnetic history of the sample can be different. The sample can be anywhere, operating anywhere, any point on the hysteresis loop. Signals will be different. So very often you have to demagnetize the whole sample and then conduct this experiment. Okay, so these are some of the sources of uncertainty. So what happens is that if you have the same defect, if you make multiple measurements, okay, or you have multiple samples, all of them are same, you think it's same, the signal is never the same. So this is the flaw variable, and this axis is the signal peak amplitude, and this is the flaw variable. So x1 is, say, the defect depth, okay, or defect size in some fashion, and this is the peak signal. You'll never get the same value every time you do it. You do it 100 times, you'll have some kind of a Gaussian distribution, where this is the mean, and it'll have some kind of variability. And these variabilities about the mean is because of all the things that we described in the previous slide. So for a larger defect, this is the defect size, you'll have a larger peak value, but again, you'll have a different distribution. So this is the PDF, a probability density function over here, a conditional probability density function conditioned on this defect. And this is the measurement based on this defect. But it's no longer a single value, but it is a PDF.
Each and every type of measurement.
Every type of NDE method. So every NDE, in industry, you don't just talk about an NDE method, you talk about the probability of detection, of different methods. And how do you determine the probability of detection? You take the two PDFs. If I just draw that along the measurement value, now I'm taking Y as my x-axis and the PDF of Y along the y-axis. What you really have is some overlapping. If the two flaws are very, very big, they can be well separated. But if this is the first one is even when there is no flaw, you're getting some signal. You'll get some small signal, and you have a PDF because of uncertainty. And this is the flaw PDF. So you can then use the probability of false rejection, probability of false acceptance. This is what you call a false alarm. This is called a missed. A false rejection means a defective sample is not rejected. So you can actually calculate all these in terms of probabilities. And this is the probability of detection. So probability of detection, if this is the threshold, you select some kind of a threshold. If it is greater than this threshold, you're going to call it a flaw. Less than this threshold, you're going to call it a no flaw. It's a good sample. But I know that the tail of this PDF is over there to the left. So you can calculate this area of this is the false acceptance. Because it is less than t, you're going to say no defect, false acceptance, or it is greater than this. It's actually the tail of the no flaw. It's a false is a false rejection. A good sample has been rejected. And I remember some time back, there was I think it was a tire company that had rejected a lot, or a wheel, aircraft wheel company. A number of, they rejected a lot of good wheels because of this problem. And typically they try to adjust the this threshold value so that this quantity, false rejection, is minimized, because false rejection means dollars for the company. That's what they want to reduce. And false acceptance, sometimes they are able, even if a small flaw, what is false acceptance? It means there is a flaw, but you're accepting it as good. So sometimes they know even if it's a small flaw, it's okay. The airplane won't break up in midair. So they allow some of those flaws to be accepted. So that is a constant. We always wonder how, and we think life is very, much more valuable. But companies think differently. They will settle the lawsuits if anything happens. But rejecting a good airplane is much more valuable for them in terms of the bottom line. So that's anyway. So very often they have this other term called relative operating characteristics. On the x-axis, you have the probability of false alarm, which they want to minimize, and probability of detection should be maximum. You want to maximize the detection, minimize the probability of false alarm. So you want to operate somewhere over here. So they try to, they do a risk analysis and see what to accept and what to do. So these are some of the concepts that industry uses, and these kind of studies can be done much easily with the model, because it's quite expensive to machine defects of different size and then generate the signals, the PDFs and all that. Yep. Yeah, ROC, that's quite a, yeah, it's the same thing. Yep. I don't know. I think it probably borrowed from some other field. Right. Receiver operating characteristics. For that, okay. Good question. Okay, it could be it's the same thing though. What we are looking at is identical, exactly the same. Maybe the word relative is not right. No.
That we were detecting a perfectly well, you can say a good sample with a defective one. We are comparing those to the relative term comes from.
It's the same thing. It's exactly the receiver operating. I basically think that's a typo. That relative should actually be receiver, because it's basically based on the receiving transducer. So I think it's receiver. It's a good catch, and I didn't catch that thing. Okay. So POD is used in optimizing a sensor design. You have different designs and you look at what the POD would be for this particular geometry and you do that thing. Okay, this actually shows how I can use the numerical model for determining POD. That was the theory of that. And you can use the model because you're doing multiple simulations for, and you're varying. For example, what is the POD with respect to liftoff variation or with respect to a particular parameter or dimension of the sensor? So you can actually model those, liftoff can be varied systematically, and you can generate what's called a transfer function, something like this. Okay. Ooh, no. So this is a forward model, and you can actually generate this PDF using the forward model because I can control the parameter, simulate, and generate the peak value and the PDF. And once I have this particular function over here, this is the most important thing, this curve, which relates how will the peak value vary with respect to the parameter that is being varied, okay? If it's liftoff that is being varied, as the liftoff increases, the parameter, the measurement decreases in some fashion. And I can use this with giving an input PDF, you can do Monte Carlo simulation and generate an output PDF. And then use this for calculating the POD. So this can be done. This is for one-dimensional POD. And there are multiple parameters varying. You can generate a multi-dimensional PDF and use that to generate your POD model. So just a slide, this was one PhD thesis, the whole thing, but I'm just condensing everything in one slide. Just to give you a big picture, the whole idea is what are the different areas of research in ND? So that's basically. Okay, the last area is inverse problems. And inverse problems, as I said, sometimes the end goal is not what is inverse problem? The input to this inverse problem is the measured signal, and the output is the defect information. Okay, so sometimes you just want a defect classification. In pipeline, sometimes they just want to classify it as class A, class B, class C, depending on the size of the defect. And sometimes they want full reconstruction of the defect shape. Okay, and the reason they want this is if it's a very pointed defect, the stresses are a lot more. Whereas if it is a rounded like a defect, you have less stress. So the remedial action will be different for the two cases. Okay, so let me just briefly, I think this is something a lot of people here are working on, signal processing and pattern recognition. So the defect classification for automated signal classification is nothing but a pattern recognition type problem. So you have your measured signal. You do some pre-processing where you do noise filtering. And there is a second step called invariance transformation. We'll talk about it a little bit. And then you extract some features. The features are fed to a classifier. This classifier can be a clustering algorithm or a neural network. Of course, this classifier has to be trained using training data. Once it is trained, it will give you, once you put the raw signal, it will tell you what the defect class is. So this is a standard signal classification algorithm. All signal, whether it is a speech signal or an image signal or NDE signal, this is a generic approach for signal analysis, right? Right? Anybody here working in signal processing, pattern recognition? You do some, okay. Yeah. So, it sort of tells you now, if you're an NDE engineer, you have to have such a wide, spectrum of knowledge to do a full-fledged system, to build a full-fledged system. And here's an example of defect classification, inverse problem defect classification thing, talked about it briefly. You have the weld, you have an angle beam ultrasonic signal. There are 4 classes. There is the volumetric class, which is porosity and slag, which are sort of globs. And there are planar class, which can be a lack of fusion, that is not fused between the parent material and the weld material. And there can be cracks, which are planar. Okay. And we saw that all the signals you do actually a raster scan on one side, because you don't have access on both sides. You can do one side. You will have the ultrasonic going in there and coming back. Sometimes you got to make sure that ultrasonics can come back from here. It can go from here to the back wall and come back. It's quite because there are people who are in communication. You know what multipath travel is. It's the same thing with ultrasonic. So interpretation, you've got to keep all that at the back of your mind. And an ultrasonic engineer knows, they just do a basic, instead of just keeping in one position, you move it around and see how individual reflections change and use that for reconstructing your geometry. So this is, we saw this in the morning. When you do a raster scan like this, you really generate an A scan, a B scan mode, and a C scan mode. And you can take, you've got to see, the A scan is a single position. B scan is you're moving it in one direction, and how does the signal change? And you also have something called B prime scan. From the 3-dimensional volume, I can take a section in this direction or this direction and generate additional type of information from there. And use all this totality of all the information to determine the defect class, whether it is crack or porosity or whatever. So because you can see, if you look at just one, this is the A scan signal from a crack. This is from a slag. So this is volumetric, this is planar. These are all experimental, not simulation. And this is the porosity. Porosity has multiple air bubbles in it. So you can see that it has a longer, and this is from a lack of fusion. Okay. So these are all experimental signals that were given, but just looking at, all porosity signal is not going to look like this. All crack signals are not going to, there's a wide variation. So you have to make sure that your system is trained for all of these. So we do have, I talked about B scan, sorry, here, and B prime scan signals. The images are quite different, but you can use some kind of algorithm for reconstructing the defect profile. But in this particular, the Navy just wanted classification, so it's much simpler problem. So looking at, this is the C-scan image, and you can see that it's very difficult to determine anything from this. But using an automated signal analysis system, we could actually find, what was this? Trying to see what kind of defect this is. Oh, yellow is porosity. It is color coded here. So this is porosity, and this particular one, you do see the two indications there, and that's the slag. Okay, and similarly, this is a crack signal. Of course, when you just look at the C scan, it's just a blob. Really, there's not much information, and the classification is not based on these intensities; is based on the full E scan. So this, so we could then classify the lack of fusion and all those things. But actually, what you see here is a part of it is lack of fusion. There's also some slag, both in the same area. So anyway, so this is the kind of, so we had a real-time analysis of all the data, large amount of data that was created by the Navy in inspecting their welds. So that's one example of an inverse problem. Yep.
Curiosity that these data that transmission collecting data, and that was being fed to that some reprocessing was done. After that, we got these images.
Right. So, you know, as I said or showed over here, in ultrasound, you are generating a three-dimensional volume. You have a raster scan over here, X and Y, and at each point you have a time data, right? So you really have a lot of data. And even though what I showed in that is just the C-scan image, we are looking at a lot of data, and then it's a holistic analysis of all that to come up with classification. No. This is, you know, it takes a lot of time to generate the data. I wouldn't call it real-time classification because, you know, it was not done in real time. The data was collected and sent to us, but we made sure that the analysis results comes out in fraction of a second. So I'm calling it real time. So, you know, it's, and then our algorithm was ported to a commercial system, ABB, you know, AM data system Navy was using. They collected the data, they did implement it. You know, I don't know how, I didn't see the final implementation. The data was being collected by the commercial system. The data was fed. So our software was integrated into the commercial software, and it would display the analysis back, the classification. So in that time, you know, it is either at least near real time. Though I never got to see the final thing. The final integrated system. You know, we gave them the algorithm, they integrated it and operate in real time.
Will be in the coming lecture, this course, the next course, we will be seeing that how that do we get the data, and from that data how to get these type of images.
Yeah, in the second part, where you have the inverse problem, where Professor Deng will focus on inverse problem, he'll get into details of these. I'm just giving a big picture, and these are some of the old projects that I worked on. So I just want to give I just want to show an example of what is defect classification. Okay, the second type of research in the inverse problems. Yes. See, condition monitoring is something that is done on a continuous time frame. See, condition monitoring, or what they call structural health monitoring, and NDE, what is the difference? NDE is like an offline completely, you know, whether it's condition monitoring or structure, it needs NDE. All this needs to be done, okay? You need to get signals, you need to interpret, you need to come out with results. Condition monitoring also does it, but usually the term monitoring is given to systems which are on a continuous, you know, mode. They ping this, for example, you have a bridge, every 2 hours they ping, they send out the signal, and they get, everything is done, you know, analyzed, and they will raise an alarm if something is wrong. So it's a different usage of the NDE system. Everything is NDE, you're right, no difference. But condition monitoring, or what they call structural health monitoring, is a little bit more because it's automatically done every hour, every day, or every week, or something like that. So, you know, there was a lot of discussion in one of the NDE conference where this new terminology like structural health monitoring or condition monitoring. Monitoring means it's done on a continuous basis. Whereas this NDE, so what happens in most industries is, let's look at the airlines. A plane has gone through 5 flights, then it is retired, taken to the hangar, you do the NDE, get it back. But if I were to embed sensors on the airplane, and as it is flying, you know, you keep getting measurements, and so they call that as the condition-based monitoring. So because there is a move in industry to move from what they call scheduled maintenance to condition-based maintenance. So even if the airplane has gone 10 times, if those embedded sensors are telling you nothing's wrong, you don't ground it and take it and do an NDE, a full-fledged NDE. So only when there is some kind of a dangerous signal there, then you say, okay, next time you better take it and get it done. So that is the way industry is using the term. But from a technical point of view, what is being done, it's the same thing. Okay, so this whole talk was on different areas of research in ND. Invariance transformation is another area. It's a signal processing algorithm. So basically, we saw that a signal changes due to the defect parameters, or it can change due to liftoff variations. The same defect, if I measure it at liftoff 1, it produces a signal. If I increase the liftoff, it's going to produce another set of signal. And when you get the when you get the measurement, you don't know what was the liftoff, okay? So the signal can change due to liftoff, or it can change due to defect parameters. So I would like, before I classify, because I'm classifying it based on the signal amplitude. The signal amplitude is small because the defect is small or the liftoff is large. So I want to make the signal insensitive to defect, insensitive to liftoff, and sensitive only to the defect, and then I can classify accurately.
Specific reason of classifying defects on the basis of size that the impact that it will create in the future, is that the only
Classifying
defects in terms of its size?
Yeah. It's the end user, whatever industry tells us. Okay, pipeline industries, they tell us, they classify all the defects into A, B, C. And A is like 20%, B is like 60%, and C is like, B is 60, and then 80%. So if it is really 20% defect, the remedial action is just reduce the pressure of transmission. But if it is 60 and 80, they will put a sleeve around it at that area. So that's why they don't care about exact size, but they just want you to classify.
That's the reason that we classify.
Yeah. Industry want to reduce operational cost. For them, ultimately, it's the cost that matters.
As an ND engineer, it's not, you can say that we are not very much interested in classifying. We are interested in getting the defect size and the location. As
an NDE researcher, you want to do the full-fledged solution. An NDE engineer will do exactly what the industry tells him to do. It doesn't matter what he wants to do. Sometimes this really happens in the nuclear industry. There was one time, again, we were identifying the size, and the power plant did not want to know if it was like 20%. They size it based on the depth relative to the thickness of the wall. So it's 20% wall thickness means it's 1/5 of it metal loss. Or so if it's a very small, they say don't tell us, because because something happens, and then the lawsuit will say they knew that they had a flaw and then they operated. So if they don't know, they say, oh, we didn't know, it just happened. So they didn't want our algorithm to report anything that was very small. Yeah, okay, so that's, well, industry has their own reasons for doing things, and they are giving us money to do what they want to do. But for our own research, we could see that a particular signal has this kind of defect. But I'm thinking that they came up with that numbers based on a lot of study. So that's the way it is. Okay. Yeah, it is. There's a lot of things that which was eye-opening for me when I work with industry. Is different from what I would do, sitting in a lab. Okay, so invariance transformation. So before I classify or interpret a signal, I have to make sure that the signal is only dependent on defect parameters and not on things like permeability, liftoff and frequency, and also these are parameters will also change the signal, but that is not, I should not be using those for interpreting if I want defect information. Okay. Yeah, in the leakage field signal, in the pipeline inspection, which usually, you have 100-mile section of pipe. It's not a continuous one single grade of steel. You have 20 feet of one steel, then the steel grade changes, the permeability changes. So as the inspection tool is going, that you're going to produce different signals, defect signals, depending on the grade of steel. So how do I make everything insensitive to permeability, right? So there are actually mathematical transformations. The only thing is, yes.
Yes, right.
This one?
Yeah. So each of them has a separate technique. Invariant which you're talking about.
Yes.
I'm trying to apply an invariance algorithm. Maybe my invariance is because of how am I going to take care of these invariances by applying only one particular method to evaluate my.
Right. Good. So yeah, this it is true when you're looking at flux leakage method, then I'm the permeability invariance is important. Okay, and because these are in the pipeline, they're all spring loaded. Liftoff variation is not so important. It is there, but not so important. In eddy currents, you have sometimes in the heat exchange tubes, you have different types of probes. Some of them spirally go up there, and some of them just go straight. You have an array of coils. So liftoff is of importance over there. So how do you make the final measurement insensitive to these permeability or liftoff? But so again, the algorithms will vary for each application, for each parameter. And this is a general approach for that. So we've seen that if you have, say, two parameters, permeability and the defect parameter, two parameters. So if I want an invariance, I have to make two measurements. I have to have two measurements that vary differently with respect to liftoff and permeability. So if I have that, then mathematically it's been shown that you can estimate a function that will take a signal which is a function of permeability as well as the defect. T is any parameter that is not relevant, and D is a defect parameter. So I take two measurements, x1 and what is it called, xa and xb, and I can find, and this function f can be estimated so that my resultant signal is a function of D alone and independent of T. So you do some extra work getting another measurement, but you can actually do this. Again, this is another PhD thesis. Okay. Yeah. So I won't get into details, but this can be done, and I'm just going to show some results. Oh, can barely see this. Maybe you can switch this light off, I think. Then, because it's, I can see it here. I don't know. I think it's a little better. This you can't.
Then switch off the complete light. Please. These two
Yeah.
slide we can have a complete off.
Yeah, I think so. I think we can take. I think it's a little better now. Yeah, you can see it. So what I show on this plot, there are two defects, okay? and 3 liftoff variations. And you can see it's a whole, everything sort of overlaps. This may be a small defect, large liftoff, large liftoff, large defect, and you can be a small defect, small liftoff. So you don't know unless you get rid of the variability due to liftoff, you cannot really interpret, classify it as a particular defect D1 or D2. And after the invariance, which I didn't describe, but there is a way to do the invariant, you can see that they collapse. From this, I generate a signal which is independent of the liftoff. I get defect D1 and defect D2. So such methods are very useful. You can really do this. Okay. So this is one example where, and I think in the signal inverse problem part of the course, he'll get into details of this thing. Okay, so that's some of the signal processing that is needed for signal classification. Okay. The other type of, those are all related to the classification. And then you have characterization. So where you want to determine the full shape of the defect. Okay. And there you can have a direct approach or an iterative approach. So here the direct approach, basically I have the full 2-dimensional raster scan, and this is the defect signal. It can be anything, it can be eddy current or flux leakage. And this is the defect profile. Okay. So this is a measurement signal, input space, output space. And so what we really need to estimate is the mapping function, a multi-dimensional, multi-parameter function that will map this to this. And again, if you have a lot of training data, I think all of you know that you can generate neural networks that will do this for you. It's just basically a function. And one of the type of neural network that we used, one of our project is what we call the wavelet basis function neural network. So neural networks, again, I won't get into this, look at it as a black box. If you give enough examples of signals from known defects, it will automatically learn to interpolate between the defects and produce the. So it's a direct mapping, and it's very fast, but but it requires a lot of training data, and if your test signal is different from the training data, we really don't know how the black box is going to perform. So that's some of the things. Okay, and the iterative approach for inverse problem is shown over here. So this is probably a more what I call a physics-based approach, because it uses the forward model. The forward model gives you an accurate, predicts the signal due to any in a defect profile. So you take an initial defect profile, apply that to the forward model, the model that is validated, which produces an accurate signal. You produce a signal, then you have an experimental signal. You compare the experiment and the model prediction. If the difference, point by point difference is less than some epsilon, I will say whatever defect profile went here is your desired. If this signal is very different from what the model is showing, you update your defect profile, go back to the forward model. So it's an iterative approach. It's but again, it is based on the physics, because this forward model tells me if my defect profile is shown is here, this will be the signal, experimental signal too. So it takes an enormous amount of time, because each time the forward model is, if it is a 3-dimensional finite element model, it's going to be different. So this is in this, for a finite element model, this is is the same slide. And this is some of the results. It basically shows the true profile and predicted profile. And they all had an initial depth profile of 10% defect kind of thing. Okay. And you can see that different profiles can be predicted very, very accurately. But again, it's you need to know you're using a 3-dimensional finite element model. So it's iterative, it takes a long time, and so on. But you don't need to train. There's no training data required. It's going through the actual physical process. Okay, so I've come down to, so what are some future directions in the inverse problem side? You want, we've seen when you use simulation models, they can be very time consuming. Okay, this is from a different, okay, that is, efficient simulation model is important. It's an important research direction for NDE. More recently, NDE of composite is now, how do you come up with the right kind of sensors and systems for composites? Then additive manufacturing. That's a whole new different paradigm for manufacturing. So how do I make sure that whatever has been manufactured has no defects in it? So you have to come up with new methods for doing something. Additive manufacturing of polymer structures or metallic structures. These are all future directions for research in NDE. Health monitoring, wireless sensors, another thing, embedded wireless sensors and communication, continuous monitoring, this is exactly what we talked about. So these are needs new kind of sensors. And if it's going to be embedded in a concrete structure, how do I find power? So there's energy harvesting, in bridges, particularly when there's vibration, you can use that for harvesting energy and power the sensors with that. So there are a lot of interesting things going on. Biomedical and healthcare, again, are different directions, because I think there's so much similarity between NDE and biomedical. So whatever we do for, in NDE can be used over there and vice versa. So, and data fusion. Data fusion is, you have two different NDE methods. So they have different kinds of information. The human being is an example of data fusion. We have eyes and nose and ears, where we have different types of information which all gets fused to get a full-fledged interpretation. So the same thing can be done with different types of NDE sensors. You can use the redundant information part can be used for noise filtering, and the complementary information can be used for increasing the accuracy of your inverse problem solution. But there are issues. So to investigate on full-fledged multi-sensor data fusion, you have, which can be done for improving the POD. There are issues like data alignment. You have an eddy current signal taken at one point, you have ultrasonic, and if you want to fuse that, you have to make sure the data is aligned. One is a wave phenomena, the other is a diffusion phenomena. How do I fuse those two? So you got to make sure data registration, data alignment, and compensation algorithms have to be developed. So those are some of the issues, and these two things are future directions. So if any of you get into NDE, there's a lot of things that still needs to be done. And the nice thing about NDE is there are not too many groups, there are not too many people who are well versed in all aspects of NDE who can come up with these kind of solutions. I always tell my students, because everyone wants to get into wireless communication, that's the in thing, but every job in wireless communication has, if there are 100 applicants, in the NDE there'll probably be 3 or 4 applicants, so your chances of getting a job is also much better. So that sort of completes the big picture. What's an NDE system? What are the different types of NDE modalities? What are the different research areas in NDE? So I'll open it for any questions, more questions, and we'll go from there.
In NDE, we have to measurement data that can be fed as an say, correction or feedback to the model that you are going trying to formulate from the analytical or the simulation, whatever you are trying to do.
Right. Yeah.
That only the measured one will help, or the only That's not the thing.
One is simulation. Simulations are an excellent replica of the actual scenario, right? Test scenario, and they do produce very accurate signals, but these signals have no noise. It's a very ideal situation. In reality, the experiment is going to have a lot of uncertainties. So you can't train a classification system based on ideal situation, because in the field, you're going to have the real world. You're going to have noise, you're going to have all those uncertainties. So it has to be a full, a mix of both for training. It's important. Sometimes, we can simulate even noise, right? And we can add that to the actual signal, use that for training, which we have done. So it is, I think it's more important to have the accuracy in terms not of just a signal, but also of the uncertainties.
To approach which kind of tools?
Say it again?
Which kind of tools are using for numerical iterative approach?
Oh, see, again, we have used both. We have developed both for different industry based on what they want. And I want problems for student thesis. So I have students who have worked, I have thesis on direct approach using neural networks, which are, that's an interesting approach too. And we have also used the iterative approach because it is physics-based, it's more academic. So we have worked on both. The iterative approach takes enormous time. That's the problem. And so most of the time, what we have given to industry, we give both to the industry and they let them pick what they want to use. But we have worked on both. I've got every slide over here is a PhD thesis.
Generally, we are using here MATLAB tool for doing operation.
Yeah. MATLAB is what we have used for most of the classification, algorithms. MATLAB is good. But when it comes to simulation and finite element, we use COMSOL. Or we also have our own software that we have developed for finite element analysis. We use that for most of our modeling. Yeah. Right. Right. Yeah. Yeah. Yeah, I think in the biomedical field, they use the term non-invasive. Here we use non-destructive, although, sometimes for the nuclear, the project that we have been doing, they do for validation. So, okay, here is the signal. My algorithm takes and predicts a profile, and we don't know what the real profile is, right? So, in order to validate the signal processing model, they do cut open. They do a metallurgical profiling, and they make sure that our profile is. And I think I will show. I thought I had some slides on that. I will be presenting that in one of the talks. How the profile that we predict and the profile that is destructively implemented is shown is the same. But NDE here is non-destructive, is like non-invasive. We don't want to destroy the structural integrity of the sample.
along with that, maybe correct, along with that, magnetic supply, that electron
Yeah.
vibration.
Yeah.
So, in parallel to that, if we see a cyclotron or magnetron which is in a microwave oven, because that movement keeps the food or something like that, whatever is being done.
Yeah.
In parallel to that movement, does it also leads to some sort of change in the material properties after a long time, or
See, the inspection is not done for a long time, right? You just do it and the power is not enough to change the material properties. And and essentially what we are trying to, it's pretty fairly low level fields that we apply. And so basically you need to have a really powerful pickup transducer that can pick up small vibrations that propagate. It just launches an ultrasonic wave or acoustic wave, but it doesn't, those things don't change property. If this was a question when they do ultrasound, imaging of the fetus, they think, sometimes people don't want to do it because the vibration can destroy or, affect, but I don't think solid materials, I don't think there's any damage done. When you compare with the actual, when you use an airplane and you look at the amount of stresses that you create, the ultrasonics, nothing. Shouldn't be a problem.
curiosity just showing about all these the running conditions of the aeroplanes and the business strategy. Does it change when you travel through flights that your mindset has changed something like that?
As I mentioned, after that Aloha Airlines, the Federal Aviation Administration, they started an aging aircraft problem and aging aircraft programs rather. And we had a lot of projects under that. And all these airlines would come and give a talk, and they, it was like a lot of collaboration with actual airlines. It was scary. It was difficult for me to get into an airplane after learning about what happened, and how airlines. If you go into an old aircraft, we could see as you enter near the door, those corners are high stress areas. And so to repair that, if there is a crack, they'll put another patch. And you could actually see those patches, some of the aircraft. And once they put a patch, you cannot detect defects anymore because, but those practice, I think it's come a long way. They have, in the years, has improved, and airlines have improved too. So, still, if you see, when you look at the statistics, how many aircrafts have you known other than that Aloha Airlines? I don't know of anything that broke midway. So it's still safe. It's safer than automotives. They say in the US, there are more people die by car crashes. So, but that was a thing. That was the first thing we all would I fly again after knowing what they do with the aging aircraft program. Really, we all went through that phase. Yeah. Is there any questions here? Oh, you're okay. So, tomorrow 10:30 next month. Okay, thank you all for patiently listening.